Right, so welcome to this solid mechanics next lecture, and what we're going to do now is the following. I'm going to just give you context. So what we've done so far is we've looked at a macroscopic problem. Okay, we started off with something like this and said, let's look at if I do this and if I cut and if I get sort of these planes here where I cut it, what do I learn from what's going on here? Okay, so breaking that into two problems, and then we said, okay, well, we zoomed out on this face and had sort of an average idea of what the stress components was, what the normals, that was good, and then we zoomed in and said, let's look at a point and say what happens at a point there, and we essentially could make sense of what's all about, and so then in the end we could essentially have sort of a stress tensor, X, Y, and Z, that could actually now relate to tractions on the face as well. So it didn't relate internally, but it also now could relate to things on the first surfaces. We know how to relate it. That was related. Okay, so that is the important aspect to understand. So that's step number one. Okay. So what we're going to learn now, or actually visit now in this block, is to say, how do I go from having this stress field now defined everywhere? So it's defined everywhere, even on these places where tractions are applied. How do I go back to these forces? And this is what we're going to be learning today, just revisiting. It's something that you should have done already in previous courses, both MO W1L1V4P1o2 and MS-10, but I want to just maybe make sure we recap that, because this is an important part of the course. This step you're going to get tested on, as well practiced on to the extreme, as you'll see for this week's tutorial. Okay, so what we need to be able to do is to say the following. How do I go from a stress tensor to a macroscopic force that's applied? Well, we know exactly how to do. We know that if we want to go from a stress tensor, the function of X, Y, and Z, okay, we might first have to evaluate the stress tensor at the right place. So let's look at this example. So I'm going to focus my energy here and say here we have now a normal N to that face. Okay, important, we have a coordinate system. This N, the NX and NY components are expressed in this coordinate system. Yeah. This force vector, its and Fx and Fy components are expressed in this coordinate system. What I have is, I want to make sure that I evaluate my stress tensor at this face where I would like to know what is the stress resultant. So first thing, let's call this distance from here to here. Let's call it XF. Okay. That is just to make sure that we sort of at that place where that force is applied. So I'm putting in that constant XF, but now I still have as a function of Y and Z. That's the first step. Okay. Next step is, I need to say, how do I take this and get to a force? Well, no, we first have to make it a traction. So I have to say, get this towards a traction. Okay, that lives at XF, Y, and Z. Okay. And this step is easy, because this step we know is just sigma dotted now with N. That's exactly what we learned before. So this is this, and then I can say next step is, if I want to get towards the force, I need to integrate. But what do I need to integrate? Do I need to integrate this whole vector, or just a component of it? Well, if you think about it, if I go from stress tensor here at this face, evaluate at XF at this face, dotted with N, I have now a traction vector that lives in this face. This traction vector could mean any direction. I've drawn it's now in this F direction, but so I need to look at what component I'm interested in. Remember, this traction vector now lives again in the XY coordinate system space. So I want to look maybe at, if I look at normals in the X direction, yeah, I want to look at the X component of this. So I want to say, take this traction vector, X, F, Y, Z, and I just want to check that I'm still on the board. Yep, this X is terrible. X, F, yo, Y, Z. I want to take specifically the X component of that. So to make it simpler, I'm going to write it as T, N, X. Okay, that's an X component of that. Now I integrate over the area of the face. And this will be equal to F for this example. Okay, so that will be the normal force, where this is now the normal X force. And what I mean with X, force in that X direction. Okay, that is important to understand. So this is step one. Okay, so this is the steps that will be required for us to do this. Let's do it on this face, and what I want to see on this face is that I indeed recover a negative F. So this is important what we want to do. So let's go and say, I'll take the stress components, evaluate it now at this face. So this face I'm going to call X minus, so let's call it F minus, X, F minus, Y, Z. Transform it. What is my N here? My N is now negative N. If I define this as N, this will be defined as negative N on that side. Okay, so sigma XF YZ dotted with negative N. So that's my dot with negative N. Next thing I need to do is to say this is now my traction. I want to take the X component of that. So I want to say take the, let's pull this out. Let's just write it like this. This dot with that integrated as take the X component. So I'm going to say sigma. I want to leave the sigma here because I want to show you that we can compare it. It's minus N dA F minus F minus the face associated with this area here. So that's A F minus the area of that face. Okay, I can pull this negative out front and say that's a negative in the front. And what I have. Now I need to compare what's going on here with what we had essentially when we had it. Ooh, did I not? Okay, so I just did the step here to what I had here. Okay, so make sure that we still write it as the X component. So I'm pulling out the X component from this product. So it's a stress tensor dotted with N, the X component of that. Okay. What I want to make sure is that we compare this to what we had here. And if you were to compare, you would see, well, I've got an N, I've got an N, I've got a sigma, and I know because it's uniaxial tension, the stress here is positive and the stress here is positive. So this is also a positive quantity. So this is quantity here, and what I actually pulled out here, it's exactly the same thing. But there's a negative there. And so what I recover now is negative F for this traction. And so this is why it's important that when you do this, please follow the steps. Traction, stress tensor traction, from traction to force. Unfortunately, often what happens is with textbooks, let me just write here, textbooks do this unfortunately often. So I just want to warn you that you don't follow that advice with textbooks. They often write it as, oh, the force is the integral of sigma xx dA, something like that. Because essentially the sigma xx would be the component that is stored there. But that's not, this is not true. This is only true if your coordinate, if your normal was in the positive direction, your normal was aligned with the x. That's the only time when this is true. So please make sure you don't just blindly do this kind of stuff. You're going to run into huge issues with signs and stuff like that. So there's just take note, there's a sigma xx dA, just for the integral of that, that's all. So please make sure that you don't follow that kind of approach that you'll often see. I think even the notes that I've uploaded from W1L1V4P1o2 might actually have that error in there, but I just want to hammer this point that you understand. If you want to go compute the stress resultants, you really have to just follow the maths that we've developed in saying stress tensor, get the traction, integrate the traction, because what we know is that the traction is an integral away from the force. Okay, they all live in this XY coordinate system. They don't live like the stress tensor in this local coordinate systems, and this is why this breaks. So this is why this is important. Okay, so this concludes the first part of this. I'm going to pause this video, or stop this video, and then I'm going to just quickly do another video where I'm not going to talk only about the normal forces, but let's talk then about what is the shear forces that we might have acting on that, and all those kinds of things. But I'm going to just remind you about these steps again. Thank you.